Welcome back, everyone. In this video, I'll be going over the lecture for the fundamental theorem of calculus. Now, the fundamental theorem of calculus, it has two parts to it. What's going to be kind of strange is that the first part is less used than the second part, but the first part actually helps you prove the second part. While we won't go through and prove them because they're really detailed, they take a lot of time, we will talk about really how we know these are true based on past sections and things we've done. But the main point is we want to be able to practice them. And the first part of the fundamental theorem of calculus, typically with the fundamental theorem of calculus, we abbreviate it FTC, and part one, we'll put a 1 after it. And it says the following. It says, if f is a continuous on the closed interval a to b, then the function g defined by g of x equals the integral from a to x of f of t dt, where x is between a and b, is continuous on a and b, the closed interval. It's differentiable on the open interval a to b, which means we can do the derivative of it as long as we're not at x equals a or x equals b. And the most important part is probably that when you do the derivative, you just get back the original function that's inside. And this really lends us to what we talked about, because remember in past sections, we talked about the antiderivative. Then we started talking about area under the curve with Riemann sums, and we kind of realized that in an example, we saw that the area under the curve, if we were dealing with velocity, gives us the distance traveled, which is like the position. And in general, this is kind of pointing us in that direction. If we want to figure out the antiderivative of something, so if you want to figure out the antiderivative of something, what you're doing is you're trying to figure out the function. When you take that derivative, it equals it. So, this is exactly what this is saying. If you look back to the definition of the antiderivative, if we do the derivative of this function, we get back the original function, right? But without overcomplicating things right now, I want to go ahead and just practice this, because what we're doing in the fundamental theorem of calculus part 1 is these things are called integral equations. And what they are really representing here is this is saying that we have a function that's actually defined by the area under the curve. And, without going into too much detail, there are examples of functions that really are defined by this in nature, statistics, physics, chemistry. Actually, the first one down here, when we get to it, is actually one of them. It's very realistic. But what this is saying is, let's pretend a and b are here. And we'll just graph the function fx, or f of t, because really what we know is the definite integral is sort of the area under the curve. And this one, whatever comes out here, is going to be the area under the curve from a to x. Well, I'm going to go ahead and just pretend f looks like this. And for the sake of using the actual letters here, I'll use y equals f of t. So this is going to be the t-axis, and this is the y-axis. And what it's saying here is that if I pick any x between a and b, so let's say x is right there, and I go ahead and the integral of this from a to x is the area under the curve. Kind of look at this as the area. This would exactly be g of x. So the area A here is g of x. Now that can be pretty confusing, but the reason is it's a formula. So x can be anything. X can be really close to A. You find that area, and that's g of x for whatever x value that is. X can be really close to B, so it's a different area, and it's still representing g of x. So the idea is it's a formula, and you can plug in many different x values to find the areas. You don't have to, just say a to whatever this is. Let's pretend this is 1 and 2. You don't have to do 1 to 1.5. You can do 1 to x and then plug in x is 1.5. That's kind of the idea here. Right, now actually using the fundamental theorem of calculus part 1, we won't actually be doing any antiderivatives in the sense of we're not going to evaluate an integral. What we're going to be doing is doing the derivatives of this equation. And the reason for that is the result is telling us that the derivative of g, which is g prime, gives us back the function inside with x basically plugged in for t. Well, if we want to get g prime in our formula, we have to do the derivative of it, so we end up doing the derivative of both sides. A couple of things I have to go ahead and mention before we work on the problems is the setup here is very important. So a is a number. It can be any number, by the way, as long as it satisfies this continuous thing, but that'll be chosen for us in the problems. And then the variable x is on the top. So it is important that the variable x is on the top and that the constant a is on the bottom. If these are flipped, so let's pretend that x is on the bottom and a is on the top, you have to use that integral property to flip the bounds or limits of integration. And I'll actually show you that in the first one. All right, so with that, I'm going to go ahead and just leave this in view while we work the first one. And we'll see that it's really not that terrible to use this. So number one says, find the derivative of the function. This is erf of x. So this is actually called the error function of x. This is a real function that's used in statistics. It's related to a normal distribution, if you're familiar with that. But it's the integral from x to 0 of e to the negative t squared dt. Now, just to clarify, the real error function is actually 0 on the bottom and x on the top. The reason I have it flipped is just to show you how you can fix it if you have it backwards. And we are told to use the fundamental theorem of calculus part 1, which means we want to make sure that the x is on the top and the number, which happens to be 0, is on the bottom here. So the first thing we have to do is flip the bounds of integration. And we know we can do that. So we can make the x go on the top, 0 go on the bottom, leave our function the same inside. Don't forget your dt, by the way, so that gives us the letter that we're integrating. But we just have to make up for it by flipping, by having a negative. That was one of our properties in the last section. All right, now, but what happens is when we do the derivative of each side, because that's really what we want to do. All right, because we want to figure out, find the derivative of the function erf of x. It depends on how you write this. Usually with functions, we just have one letter, so we can put the prime. You can still put the prime on the erf part. Now you have that negative sign up here, so that has to stay. But this is the exact setup we have in our fundamental theorem. It says that if your bounds are from a number to just x, then all you have to do is plug in x to the inside. So let's go ahead and actually write that down before we do it. So it's just x on top and just a number on the bottom. So what do we do here? The fundamental theorem of calculus part 1 says when we figure out the derivative of the function, so in our case here, the erf, it's called the error function, all we have to do is actually plug in x in place of t, because that's really all this is saying is the derivative is f of x. Well, I'm going to go ahead and erase that just so it doesn't confuse, but really what we're doing is just taking the x and plugging it in for t. Now you can have any letters. What you're doing is you're plugging in the letter on the integral inside for the letter in the function, but you very literally plug it in. So that's all you have to do. It's e to the negative x squared. And that's it. For this one, there's nothing more to it. Now we could even make these types of problems a little bit easier by giving you the x on the top. So if x was on the top and 0 was on the bottom, you wouldn't have had to do this flipping. So there wouldn't be a negative sign here. It would just be e to the negative x squared. Right. Now, of course, it's possible to have different things. So we can have something a little different. You'll see the next one here. It says find the derivative of the function of h of x equals 1 to integrate from 1 to e to the x. So it's not just x, it's e to the x now, of 2 times the natural log of t dt. And once again, we're told to use the fundamental theorem of calculus, part 1. So we're going to make sure we're basically plugging in. Now we do have the number on the top, or sorry, the number on the bottom, and we do have the x on the top. So from that aspect, we're in a really good spot. We have the number on bottom. We have something with x on the top. It's not just x. So what you have to do is make a slight adjustment. And after this one, you can kind of remember it as doing the chain rule. So if the top is not just x, what you do is you replace, and you don't have to go through this step once you see it. If you kind of see the pattern, this is just to explain what's going to happen. You replace the top with just the letter U. You can use any letter you want as long as it's not used in the problem. U is the typical one. So we replace the top with U. And so we have h of x equals 1 to the u of 2 times the natural log of t dt. Right. Now at this point, I really haven't done anything by just saying I'm replacing u or e to the x with u. So I'm going to go ahead and just actually write that down on the side. That was our substitution. Right, but when we do the derivative, because now we are in a position like before, we have just the letter on the top, comparing it to the above here, it is not x, it's u, so we do have to be careful eventually, but it's just a letter on the top and just the number on the bottom. And once again, it doesn't matter what the number is, as long as we respect the continuity thing, and we do, because the natural log, we can have 1 inside, so that's fine. So we would do the derivative, and we got h prime of x equals, and when we do the derivative and we do this plugging in, we get 2 times the natural log of u. But what's going on here when we're doing the derivative is we're doing the derivative with respect to x. Well, when we do the derivative, we're kind of like with this u, we're not just doing the derivative, or we're not just plugging in, there's a derivative going on here. So since we didn't plug in just x, you must use the chain rule to multiply by u prime, the derivative of what you plugged in. So remember the chain rule, we've done it a long time now, so it may just be like second nature and we're not used to seeing it like this. But the chain rule says whenever you do the derivative with respect to a letter, if the thing that's being plugged in, the thing that's on the inside is not that exact letter, so it could have been just like 2x or a completely different letter like u, we must multiply by the derivative of the thing that's being plugged in, and that is u prime. All right, so this is technically not wrong. You just actually need to plug in, because we started with x's. Our function has x in it, so we want x's, which means you need to plug in what u is and plug in what u prime is. And u prime, at least the derivative of e to the x is itself, so it's easy to plug in. We have 2 times the natural log. In place of u, we have e to the x. And then times u prime, which is also e to the x. And now this one you can actually simplify further, because we know the natural log and the e kind of cancel out in this situation, leave us with just the exponent. And our final answer here is 2. The x is all that's left in this side here, so we got x, but then you got e to the x on the outside. So what ultimately happens here is when you don't have just x, what you're doing is you're basically plugging in the thing here, because we really did just plug in e to the x. If you look at this visually, is what we did. If we had taken our original without knowing to do the chain rule thing, we would have plugged in e to the x, which would have given us this part. But then because the thing we're plugging in is not just x, it was e to the x, we multiply by the derivative. And maybe a little confusing just because the derivative e to the x is itself, but we're not plugging in e to the x. This was from the derivative, u prime. All right, so a very important idea when you use this one, use the fundamental theorem of calculus, part 1, is when you don't plug in or don't have just x on the integral, you go ahead and just multiply by the derivative from the chain rule. Right, so if you're getting those wrong on the practice problem or something like that, you're probably just forgetting this part. Think to multiply by the derivative of the top. All right, so the last example here, just because we want to go and cover all of our bases, is you can still use the fundamental theorem of calculus, part 1, if you have letters on both bounds. Okay. And the idea is broken into two parts like this. Since we have letters on both bounds, one's x and one's x squared, but they could be cosine of x and sine of x, just things with x. Well, what's not going to help us is flipping by using a negative. And that's not going to help us because we're still going to have an x on the bottom and x on the top. So what you do is you can split into two integrals. And what you do is here is you just pretend, or you can let a, because you don't want to specify a number here, let a be any number between x and x squared. Now we don't know if x or x squared is bigger, so we're not saying that, you know, x, this a that I'm about to write is between x and x squared as far as it, x is the smaller one, x squared is the bigger one, it's just a number between them. So what we do is we go ahead and we use a property of integrals. I'm going to go ahead and take my original integral, dt, not dx. All right, so one thing that we mentioned in the past, and I guess I'll go ahead and reiterate because I almost wrote the wrong thing, is that the dt, that's the letter of the thing you're integrating. This would not be dx because we want x, we'd have to have x inside and we have t's inside, so that's why it's dt. All right, but what we're going to do here is we're going to write this and basically break it apart as two integrals, from x to a, and then from a to x squared. Right. Now, we're used to the property from the last section is this going from right to left. But the way you want to think about it is we're finding the area from x to a, and then we're finding the area from a to x squared. Right. Well, if we're doing that, then that's the same thing as finding the area from x to x squared. So it should make sense. Now the point here and why you do this is now at least each integral has x and spot. This one's on the top, which is good. And this one has the number on the bottom. That's the setup we need. And here, the first one, we have it flipped, but we can do what we did in the first problem and just flip it by making a negative sign. So, you know, in this one, we have x to a, x is on the bottom. You just do the same idea here. Flip it, make a negative sign to get it right. All right, so let's go ahead and do that. And once we flip it, then I'll do both parts. So let's go ahead and say this equals negative the integral from a to x. So we're flipping the bounds. Nothing else changes here. And I'm not doing anything to the other one because it's already set up well for me. And what we can do now is do the derivative. So actually, let me use a different color like I've been doing just to make it clear. So let's go ahead and do the derivative. Now remember, this was called f of x, capital F of x. So we do want to make sure we're doing the name correctly. Capital F prime of x. Well, when we do the derivative, we know the setup because of the previous two problems. We leave the negative sign there because it's just out front. When we have just x on the top and a number on the bottom, all we do is plug in x in place of t. So we get cosine of x squared. So the first one here is set up perfectly for us, just a number on the bottom and x on the top. So we just have to plug in x. Plus, now the second one is not just x, but we do what we did in the previous problem. We still plug it in. So we're going to plug in x squared for t, the entire thing. We have x squared, and then it's squared because we have t squared. But because of the chain rule, we have to multiply by the derivative of x squared, which is 2x. Right. And you're pretty much done here. All you have to do is really, I would just simplify this. X squared is x to the fourth. So you got negative cosine of x squared plus, and I'm going to put the 2x in front here just to make it a little prettier, 2x times cosine of x to the fourth. All right, now definitely this last example, not a lot of integral equations are defined with their bounds like this, but they can be. And I wanted to make sure we are thorough. But there are plenty of examples like the first one, where this is actually a function that you won't be able to quote unquote integrate, as we're about to establish in a minute with the second fundamental theorem, second part of the fundamental theorem of calculus. And this is the best you can do to make that equation. So these are relevant, especially if you do statistics, physics, you will see them, and you don't have to be at an extremely high level of class in those fields to actually see them. So the way people typically work with them is they work with their derivatives because they have a formula, and then they try to understand their derivative to understand the original. Right, but that's the first part of the fundamental theorem of calculus, and we'll stop there. Now, I do want to emphasize what I said before is that the second part is more important for us. We won't run into a lot of integral equations in our math class, but you do want to make sure that the way you basically work with them is doing their derivative and understanding the derivatives equation. But I'll see you in the next video.